millisecond to get there. Once again, it's on page P9. So get to your McGraw-Hill book.
Where did you find the Zoom meeting? Did you go to the Google Classroom? Actually, it's not posted it on my now. Oh.
Okay, anybody having trouble accessing the McGraw-Hill or anything like that? Or are we pretty good on the tech side of stuff? Okay, perfect, perfect. Okay, and these are the examples that we're going to walk through. So you can see the first one. We're given the function 2x squared minus 8x and plus 4, and we are asked to graph this by making a table of values. Okay, and this is, you can all do this very simply, very easily. We just got to understand that there's a quicker way. So the first thing we're going to do is we're going to walk through this, how a person who doesn't have any understanding of a parabola and how it works, how they would probably solve this. How would they graph it? Okay, we're going to use the points 0, 1, 2, 3, and 4. Okay, so there's my ordered pairs. You can do it in ordered pairs. You can do it as a table. We're going to be graphing it there as well. And what we want to think of is we're all familiar with function notation, right? We know that since we are given these x values, and we're given those in this example, and they want us to graph it making a table of values, that tells us, hey, we want to plug those in, right? The easiest one to plug in is going to be 0, probably 1. 2, 3, and 4 is going to get a little complex, but it's not going to be the end of the world. So let's look at 0. And 0 also corresponds to where on the y-axis we're going to fall. Okay, remember it's called your y-intercept. Very key thing, makes it one of the quickest, easiest points for you to graph, and that's because anything times a 0 is 0. So what we would do is we would plug in 0. So we're going to have 2 times the quantity of 0 squared minus 8 times 0 plus 4. So with knowing that anything times a 0 is 0, so 0 times 0, because it's squared, is 0, times 2, that's equal to 0, minus 8 times 0, which is also 0, and then plus 4. So 0 minus 0 plus 4, that's going to give us the point 0, 4. And you can see we got that just by plugging it in. Another way that we could write this, oh, I didn't want to erase the whole thing, dang it. 2x squared minus 8x plus 4. Another way that we could write this for is that f of 0 is equal to 4, and actually use function notation. But function notation is saying, hey, we plugged 0 into our equation f of x, meaning that we plugged a 0 in every situation where we saw an x, and we were yielded 4. Okay, so once again, we're just plugging them in on this first one. So the second one, for the point 1, we'd have 2 times the quantity of 1 squared minus 8 times 1 plus 4. Okay, 1 times 1, because it's squared, is 1, times 2 is going to give us 2. 8 times 1 is 8, so 2 minus 8 plus 4. So 2 minus 8 is a negative 6, plus 4 is equal to a negative 2. Okay, and once again, you can see the pattern. We are just plugging these in over and over and over again. So once we get to 2, we have 2 times the quantity of 2 squared minus 8 times 2 plus 4. 2 squared is 4 times 2 is 8 minus 8 times 2 is 16 plus 4. We get 8 minus 16 is negative 8 plus 4 gives us a negative 4. So our point at the x value 2, our y value is negative 4. Now the next one is 3. So 2 times the quantity of 3 squared minus 8 times 3 plus 4. Then we use our order of operations. 3 squared is 9 times 2 is 18. Minus 8 times 3 is 24. Plus 4. 18 minus 24 is negative 6. Plus 4 is a negative 2. And then our final one is the point 4, or the x value 4. So we have 2 times the quantity of 4 squared minus 8 times 4 plus 4. 4 squared is 16 times 2 is 32. 8 times 4 is 32, then plus 4. So 32 minus 32 plus 4 is equal to 4. 32 minus 32 is 0, plus 4 is 4. So we have a table of ordered pairs. Our x values are on the left. Our y values are on the right. And you can see they're 0, 4, 1, negative 2, 2, negative 4, 3, negative 2. If I wanted to plot these, I could do it very simply. I would take my y-intercept first. It's going to be on the y-axis. Count 1, 2, 3, 4 up. So I have a point there. At 1, I have negative 2. So I have a point there. At 2, I have negative 4. So I have a point there. 3, negative 2. I have a point there. And 4, 4. I have a point here. And my parabola that tape's hard to write on. It's going to look something like that. Remember, I'm not Picasso. So my drawing's a little bit skewed. I think it's because my XY plane is pretty big. Okay, so this is generally what we're going to look at. Okay, these are where all of your graphs are. They're all going to be in this U shape. But there's a couple items that we need to address. Okay, the first one is the lowest possible point, or what could be the highest possible point. That's known as your vertex. Okay, it's the lowest possible y value or the highest possible y value, depending upon whether your graph points up or points down. Okay, in this case, our graph points up, so our vertex is the lowest one. This can be known as a maximum or a minimum. Okay, and when you're talking about max or min, you're talking about y value. But the cool thing about this is this also provides what's known as the axis of symmetry. Okay, and the axis of symmetry is what allows you to quickly graph these. Okay, it allows you to do half of the work. And the reason is is because through the vertex x value, if we were to draw a dotted line that goes all the way through it, we can see that we've effectively broken our graph in half. Okay, this left side of the dotted line mimics exactly this right side. Okay, or if you can't really see this very well, you can see it when you're looking at your points. 2, -4 is our vertex. And then if you look, our y values are the exact same as long as we have equal distance from the vertex. So since our vertex value is 2, if we were to go 1 unit right, that would be to 3. You can see we have the value of -2. If we go 1 unit left, we also get the same, the y value of -2 because they're equal distant away from the vertex. We take 2 spots left, we get the point 0.04. And if we go 2 spots right, we get the point 0.44. You can see that our x values are equal, or our y values are equal as long as we are equal distant from the vertex. Okay, so each one of you should have seen a parabola, but this is the long way of how to graph it. Plugging in each individual x value, getting their y value, and then graphing them. Okay, as you can see, that takes a wealth of work, takes a lot of effort, and especially if you're using very big numbers or possibly decimals, can get pretty hairy. Okay, it's not the most efficient way to do it. It's one method of how to do it. That's how somebody who just knows what function notation would probably graph it. Okay, they'd spend time plugging it in and taking it out. Okay, but that is your example 1. And that brings me into a perfect key concept, which is at the bottom of page P9. Let me zoom. Okay, and it's the graph of the quadratic function right there. Take a minute and analyze that while I'm erasing, and we'll go. Okay, so it says key concept, graph of quadratic function. Consider the graph of y equals a squared plus b squared, ax squared plus bx plus c, where a cannot equal 0. The y-intercept will always occur when x is equal to 0. Okay, that's the place of where it is going to cross the y-axis, and that's because the y-axis is located where x is equal to 0. So in order to find the y-intercept, we would always plug in 0. But then the key thing is the equation of the axis of symmetry is equal to a x is equal to a -b over 2a. Okay, and then it says the x-coordinate of the vertex is equal to -b over 2a. This is useful because, like I said, this is what allows you to graph these much more efficiently and to utilize the axis of symmetry. Okay, this is a key step in order to be efficient. Not saying that plugging them all in and doing them the long way is wrong, because it's not. You still get the same answers. Just like I said, it's not the most efficient method. Okay, it's much more efficient to use the axis of symmetry and the y-intercept in order to find your points. So now we're going to go to page P10. And we're going to work on example 2, where it asks us to use the axis of symmetry and the y-intercept and vertex to graph. Okay? So what we are given as an equation is x squared plus 2x minus 3. Okay, so our equation is there. And they're giving us step 1, which is to determine A, B, and C. So looking at our equation, the coefficient that is associated with x squared is always A. In this case, most people would say that it's a 0. Understand that that is incorrect. If it's just the variable with the exponent, your value of A is always 1. So it's really 1x squared. The value of B is what is associated with just the single x value, not x squared. And that can be 0. If it's 0, it'll be omitted. And then you have C, which is referred to as the constant. And you'll find that your value of C will always turn out to be your y-intercept. That's because when we plug in a 0 here for x squared and a 0 into x, those are going to turn out to be 0. So in this case, I'm predicting that we'll have a y-intercept of -3. Okay, so after you have identified those points, what we want to do is we want to use our equation for the axis of symmetry, or the x value of the vertex, to find out where that falls. Okay, and we're doing that because that's going to determine where our graph is to the left or to the right, right? And if we use it strategically, we can minimize the amount of work. So in this case, I have a b value of 2, and I have an a value of 1. So if I plug those in, x is equal to a -2, because b, and then 2 times 1. So that's going to simplify to a -2/2, which will simplify down to a -1. Okay, because our numerator and our denominator are the same. So in this situation, you can see we get the x value of our vertex as -1. Okay, and here's where we want to be strategic. We know our graph is going to be symmetrical about this line right here. So to use this efficiently, I want to plug in points that are close to this. Okay, I want to plug in points that are close to this. So if -1's here, a good point to pick would be -2, -3. I'd also go 0 and 1. Okay, picking out 5 points. Okay, so now I know where my graph is located left to right. I've picked out my 5 points, but the next thing that I got to do is I got to figure out where my vertex falls. What's the y value of it? Because that determines the maximum number or the minimum number. In this case, it's going to be the minimum number because my graph is going to be opened up. Okay? In order to do that, I'm going to take this point, this -1 that I got from my vertex, and I'm going to plug it in to my original equation. Okay, so I'm going to be left with -1 squared plus 2 times -1 minus 3. So -1 squared is 1. 2 times -1 is a -2, and then a -3. So I have a +1 minus a -2 gives me a -1. Now I'm going to minus 3 more. That's going to give me a -4. Okay, so my vertex point is right here at -1, -4. Okay, and once again, that determines my min value. So my rest of my points are going to be higher than -4. Okay, and here's what I was talking about, being able to do half of the work, using the axis of symmetry to do half. Okay, the next easiest point to plug in is 0, my y-intercept, because it's going to cancel everything out and my constant's going to be left as the y-intercept. So I'm going to plug in 0 first. Okay, so I get 0 squared, then plus 2 times 0, then minus 3. 0 squared is 0. 2 times 0 is 0, minus 3. So 0 plus 0 is 0, minus 3 is a negative 3. And my y-axis point is right here. But this is where the axis of symmetry makes it very easy for you. I've been given the point 0, negative 3, and it is 1 to the right of my vertex. Okay? So since my graph is symmetrical, I already know what the point 1 to the left is going to be, because it has to be symmetrical. So if 0, negative, if the x value 0 has the y value of negative 3, the x value of negative 2 is going to match that. So at negative 2, I'm going to have a point at negative 3. You can see that they are equal distant away from my axis of symmetry, and they are going to be equal distance, or they're going to have the same y value. So this is how you really do half of the work. I don't have to plug in negative 2. I can, but I don't have to, as long as I trust the process. Because in order to prove it, you would have to plug it in. So we'd have negative 2 squared plus 2 times negative 2 minus 3. Negative 2 squared is 4 plus a negative 4, because 2 times negative 2 is negative 4 minus 3. You can see 4 plus a negative 4 is 0. Minus 3 gives you the y value of negative 3. Okay, so just reinforcing it. I didn't have to do that step if I trust my axis of symmetry. Okay, so you can see how it makes you much faster. And now it's just time to finish off my parabola. I can use negative 3 or I can use 1. It's really based upon your personal preference. I'm going to choose the one that's easiest, right? I want to be fast. I want to be efficient. Negative 3, squaring it, multiplying it, that can get a little hairy. Using 1, anything times 1 is itself, that makes my life very, very easy. So I'm going to plug in 1 squared plus 2 times 1 minus 3. So 1 squared is 1 plus 2 times 1, which is 2, minus 3. And I get 1 plus 2 is 3, minus 3. My y value is going to be equal to 0. And since it is equal distance away from the vertex as negative 3 is, I know that that point is also at 0. So I have 1, 0, negative 3, 0, and my parabola is going to look like that. Okay, with the vertex or the minimum value at negative 1, negative 4. So you can see very quickly, very easy, that being able to use the being able to find the x value of the vertex and the axis of symmetry, it just makes you so much faster. It makes your life easier. That's why we focus on it. Okay, so a key concept, being able to use this information. Okay. Let's make sure I'm on the right page. Got it. Okay, the next key concept. Talking about your minimum or maximum values. Okay. So maximum and minimum values, they work from the vertex. You can see on the left here, we have a minimum value, and that is because our value of A is greater than 0. Okay, on the graph on the right, we have a maximum value because our value of A is less than 0. So in other words, how does our graph begin? It's always going to begin with the value of A. It's just a matter of, hey, is this negative? or hey, is this positive? If the value of A is positive, you have a minimum value which limits your range. Okay, nothing will go beneath the y value of the vertex. If we have a negative A value out front, then we have a maximum. This is the highest point of our graph. Okay, so all of our other y values are going to be less than it. Okay, and it also determines whether our graph opens up, so for a positive A value, or if it opens down for a negative A value. Why is this information useful to you? Well, for one, it gives you a built-in check. As you're plugging in points, if you know that, hey, my vertex is a minimum value, and I plug in an X value and I get a Y value that is less than that, it's probably a hint that shows, hey, I might have messed up my arithmetic, okay, because that doesn't add up to the facts that I already know. I know I have a minimum. This should be the lowest point. Why, when I plug this in, am I getting a point that's lower than it, right? So it's a built-in double check. Okay. And now we are off to example 3 on page P11. Okay. So it says, consider the graph f of x is equal to a negative 3x squared plus 12x plus 11. So negative 3x squared plus 12x plus 11. Okay, and then it says determine whether the function has a maximum or a minimum value. And we can determine that just by looking at it. Okay, so our value of A is always the one that's associated with x squared, right? So in this situation, 3 or negative 3 is less than 0. So that tells us that, hey, we're going to have a maximum value. And our graph is going to be opening down with the vertex at the top. All right? Let me label my graph so that I can graph it. Okay, now looking at number B. It says find the maximum or minimum value of the function. Okay, so remember our minimum or maximum value always occurs at the vertex. Okay, it's always going to occur there. So in order to find that value, first we have to find out where our x value of our vertex is. Where's our axis of symmetry? Right, so we're going to use x equals a negative b over 2a. And we're going to plug in a, b, and c in order to find this. So we have x equals negative 12 over 2 times negative 3. Okay? So 2 times a negative 3 is a negative 6. So in all reality, it's a negative 12 over a negative 6. I have 2 negatives here, so they're going to cancel out to give me 12/6 or 2 over 1 after simplifying. So the x value of my vertex is 2. Okay, that's also where my axis of symmetry is going to come in. So on my graph, I know that this value here is where my axis of symmetry is. Okay, but I'm not done yet. I found my x value. Now I have to try and find my y value. In order to find my y value, I have to plug 2 into my original equation. So I have a negative 3 times a quantity of 2 squared plus 12 times the quantity of 2 plus 11. So 2 squared is 4 times a negative 3 is a negative 12. 2 times 12 is 24. So that's plus 24 plus 11. Negative 12 plus 24 is 12 plus 11 gives you the answer of 23. So my vertex is at 223, which would be way up here. I'm going to count by 5s on my y-axis. That way I can plot it. So 2, 5, 10, 15, 20 would be roughly about right there. And once again, that's a maximum value. My A value is negative, so my graph is going to go down. Okay, the way that we would finish out this graph is we would plug in certain other points to make it easy. And for a parabola, 5 points is expected. 3 points gives you a good idea. Okay, so I'm going to plug in a 0 and a 4 because those are going to be the easiest values for me to work with. Okay, so 3 times, or a negative 3 times 0 squared is 0, plus 12 times 0 is still 0, plus 11. So my y-intercept is 11, and you can see that it is also my value of c. The constant will always be the y-intercept. And because I know how my axis of symmetry works, I'm 2 away from my axis, I'm 2 away from the vertex to the left for 0. So I'm going to go 2 to the right. And my graph has a point at 0, 11. And 411, and it looks something like this. Okay, but now we have to ask ourselves, it's awesome that we can graph it, but did we answer the question? What are they asking us for part C? On part C, they're asking us what is the domain in range? Okay, so first when you're considering the domain, remember that the domain corresponds to all the applicable x values. If we plug in an x value, are we going to get an answer? Or is it undefined? Okay. For any polynomial that does not have division, or any trinomial, what we're going to have here, our domain is all real numbers. Okay, and more or less, that's what it's saying, is that it doesn't matter how far I go to the left, I'm still going to get a y value when I plug in an x value. And no matter how far I go to the right, I'm still going to get a y value when I plug in an x value. So for a polynomial, the domain is always all real numbers, unless it is being divided, because then you can run into a situation where it is undefined. Okay? But now we have to consider the range. It's all the possible y values. This is where your maximum and minimum comes in. Remember, we had a negative a value, so we said that we're going to have a maximum value because our graph opens down. We found our vertex using our equation negative b over 2a, and we found that our vertex is at 223, way up here. So if that is a maximum value, are we going to ever have a value that's higher than it? Are we going to have 24 as y value? The answer is no, because if that were the case, this wouldn't be a maximum. Okay, maximum means it cannot go above. It has maximum capacity. Okay, so this is useful when you're talking about your range. That means y is less than or equal to 23. Okay, y is less than or equal to 23 as our range. couple things that you'll have to do is finding the vertex and then being able to state domain and range. But if you stick to this process, like I said, it makes you very quick, makes you very efficient, and it gives you all the information you need. It's going to give you your maximum or minimum value, which corresponds to your range. And remember that your domain is more than likely all real numbers. Fix that part. Now we're off to factoring. Okay, we're still on page P10, but now we are going to talk about, or not P10, P11, and now we're going to talk about the zero product property. Okay, and once again, that's page P11. Looks something like this. Okay. So if we read 2, it says solve quadratic equation. A quadratic equation is a polynomial equation of degree 2. The standard form of the quadratic equation is ax squared plus bx plus c is equal to 0, where a cannot equal 0. The factors of a quadratic polynomial can be used to solve the related quadratic equation. Solving quadratic equations by factoring of application of the zero product theory. So the zero product property, it states that for any real numbers, a and b, if a and b equals 0, then either a equals 0, b equals 0, or both equals 0. And that's because anything times 0 is going to be 0. So in order for a times b to be 0, one of them has to be a 0. Is more or less to solve, to sum that up in layman's terms. And you can see that we are solving by factoring. First, you got to ask yourself, what does it mean to solve? So we have x squared minus 8x plus 12. Okay, and that is set equal to 0. Okay, and I'm going to use my graph here that I have just to show you an example. So if I were to extend it so that it crosses my x-axis, when it's talking about solving, you're looking for roots or zeros. Okay, what a root is all the places where y is equal to 0. Or in other words, we're looking for our x-intercepts. Okay, it's these points. That's because we're equal to 0. So what we're going to try to do by factoring is we're going to break these into 2 binomial terms, set them equal to 0, and then solve to try to figure out where that x value falls, which makes y equal to 0. Okay, so they've given us x squared minus 8x plus 12, and they've asked us to solve by factoring. Okay, so the first thing, if you remember from last year, I always like to draw my box. It's a very helpful method. Okay, first thing I'm going to do is I'm going to bring my value of a up into the top left, inclusive of the variable. So it is x squared or 1x squared. It goes top left. The next thing that I'm going to do is I'm going to take my value of a. You good? Yeah, I'm good. Okay. And I'm going to multiply that by my value of c. So since a times c, 1 times 12 is equal to 12. That value goes into the bottom right, okay, or the value of c goes into the bottom right. Now, I've already multiplied them, so I know that they equal, or when multiplied, they go into 12. So what I want to ask myself is I want to find 2 integers that can be negative, that are going to multiply to equal a positive 12, but are going to add to equal a negative 8. Okay, so I'm trying to think of integers that fit that, and the two that jump into my head are a negative 2x and a negative 6x. Okay, and I'm going to fill out my box. Now, I'm going to use row 1 and row 2, column 1 and column 2. I'm going to factor out the greatest common factor. So the greatest common factor between x squared and a negative 2x is x. The greatest common factor between a negative 6x and 12 is a negative 6. Now looking at my columns, x squared and 6x, still just going to give me x. And then negative 2x and 12 is going to give me a negative 2. The reason I like the book method is because it allows you to double check yourself. So I think I have my binomials. I just need to verify that. So negative 2 times negative 6, if I drag and where they meet is where they're multiplied. So negative 2 times negative 6 is 12. Good there. Negative 2 times x is a negative 2x, so I'm good there. X times x gives me x squared. X times a negative 6 gives me negative 6x. So I've passed my book test or my box test, and my binomials are x minus 6 and x minus 2. From the zero product property, it states that one or both of these need to be equal to 0. So we're going to set them equal to 0, and then we're going to solve for our x values. Solving the top one. I have x minus 6 is equal to 0, so I plus 6 from both sides. And I'm left that x is equal to 6. Solving the bottom one, x minus 2 equal to 0. I'm going to plus 2 to both sides to solve, to isolate my variable. And I can prove that x is equal to 2. So what this is saying is that when I plug in the x value 6, I should get a y value of 0. And when I plug in the x value of 2, I should also get a y value equal to 0. So we're going to prove that just by plugging it in. So starting with 2 because it's easier, 2 squared minus 8 times 2 plus 12 is equal to 0. 2 squared is 4. A negative 8 times 2 is a negative 16. Plus 12 stays there. So 4 minus 16 is negative 12. Plus 12 is equal to 0. So x minus 2 is in fact a root because when I plug it into the original equation, I get a y value of 0. And then the second one of 6. 6 squared minus 8 times the quantity of 6 plus 12. So 6 squared is 36. Minus 8 times 6 is a minus 48 because 8 times 6 is 48. Plus 12. 36 minus 48 is negative 12. Plus 12, once again, is equal to 0. And that gives me my roots. Okay, once again, your roots are where we cross the x-axis. We're looking for our x-intercepts anytime that it says solve. One of the quickest and easiest methods is to factor. Okay? But that brings us to our last one, and that's in situations where they are not factorable. And we are still looking to solve these equations. And this is where we use what's known as the quadratic formula. Okay, and what the quadratic formula is it is a formula that will give you roots when the situation is non-factorable. Okay, and a good example of it is on page P12, about midway down. Okay. Let me share my screen real quick. And what it says the solutions of a quadratic equation for the term ax squared plus bx plus c equals 0, where a cannot equal 0, are given by the following formula. And it's listed right there. It says that x squared, or x is equal to the opposite of b, or negative b, plus or minus the square root of b squared minus 4ac all over 2a. Okay, when I was in high school, the easiest way for me to remember it is that it had a little jingle that went to ring around the rosy, pocket full of posies. Or in other words, how you would say it is that x is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a, just like that. Okay, sorry, I'm not a singer, but it's a helpful way to remember it because it fits that jingle pretty well. Okay, and the example that we're going to work on is example 6, and they give us x squared minus 4x plus 15. So x squared minus 4x plus 15. The first step is to identify your values for A, B, and C. So A, once again, is just a 1 because it's x squared by itself. B is a negative 4, the coefficient that is associated with x. And C is our constant of 15. So we have them identified. Now we want to plug them in. So x is equal to a negative 4. So those for B, x is equal to a negative b. It's also referred to as the opposite because whatever you plug in there is going to have the opposite sign when you're working on it. So if it's a negative, the negatives cancel out, and this is going to turn into a positive 4. If it was a positive at the beginning, so like x squared plus 4, then we would just use negative 4. So x equals the opposite of b, plus or minus the square root of negative 4 squared minus 4 times 1 times 15 all over 2 times 1. Okay, and the next thing that we want to do is we want to start taking care of our multiplication and simplifying it. That way we're going to be working with updated information. So x is equal to a positive 4 because it's the opposite of a negative, plus or minus the square root of 16 minus 4 times 1 is 4 times 15 is 60 all over 2. Well, they really did not give this an easy one. All right. So now we can take care of our addition and subtraction because we've taken care of our multiplication. So x is equal to 4 plus or minus the square root of negative 44 over 2. Okay, here a problem's probably jumping out at you, and it's that we have the square root of a negative 44. Square root of a negative 44. If you remember from your properties of radicals that we covered in Algebra 2, this negative 44 can be split into the square root of 4 times the square root of 11 times the square root of negative 1. Okay, it's called the power property of radicals. We can expand that. And we want to expand it so that we have a perfect square. Okay, so 4 is a perfect square. If we multiply all these together, we will get negative 44. Okay, so to help ourselves solve it, we're going to break these down. The square root of 4 is equal to 2. The square root of 11 is an irrational number. Therefore, we're just going to give the exact example of the square root of 11. And the square root of -1 is I. Okay, so this -44 can really be written, or the square root of -44 can be written as 2i times the square root of 11. That's going to be added to 4 plus or minus over 2, and those are equal to our x values. Okay? Now the last step. So we've taken care of this. The last step is to break our plus and minus apart. So we have plus minus here. What that means is that our x value is equal to 4 plus 2i in the square root of 11 over 2. And x is equal to 4 minus 2i square root of 11 over 2. And now we want to simplify it. Okay? Notice that 4 and 2 can be simplified because they are both constants. This 2 and 2i square root of 11 cannot be simplified. Okay, they cannot be simplified. Oh, never mind. They can, because it's multiplication in your division. Okay, so we can simplify this 2 into both of them. And 4 divided by 2 is equal to 2. These 2's are going to cancel out. So we are plus square root of 11i as an answer. And then the same thing on our subtraction. 4 and 2, 2 and 2 can be simplified. So we have 2 minus square root of 11i. Okay? And what this means are two answers. What do they mean? Okay, you notice that we had to use the imaginary coefficient of I. So that tells us that our original graph, x squared minus 4x plus 15, does not really touch the x-axis. Okay, it does not touch the x-axis. Or in other words, these are imaginary roots. We can still find them using the quadratic equation, but they are imaginary. So in all reality, this graph does not have x-intercepts, but it can be solved. So this time, any questions? Any questions before I get you to your assignment and turn you loose? Okay, just a couple more minutes for questions. And I'll walk you through the assignment real quick. Okay, so your assignment is posted into Seesaw. Right here it says page P13, numbers 2 through 28 evens, 36 through 40 evens, 42, 40, 44, and 48. Okay, these are going to correspond to what we have done today in class. Let me make it big and let me get to page P13. Okay, so here's page P13. You can see that you're going to start off by graphing. So graphing by making a table of locations, values. Once again, use your axis of symmetry. Make yourself more efficient. Okay, and then 8 through 12, once again, still graphing using your axis of symmetry. 14 is another graph. 16, determine whether each function has a maximum or minimum value. Okay. Then state the domain and range. So for 16, you can see it's going to be a minimum. Okay. And the domain is going to be all real numbers. And it looks like your range is y is bigger than -2. 24 through 28 down here are solving by factoring. 36 through 40 is solving using the quadratic equation or the quadratic formula. And then 42, 44, and 48 are just solving, trying to find the roots. So on this assignment, whenever it says solve, you're looking for the x-intercept. Okay, you can do that by graphing, factoring, or the quadratic formula.